Example 3 in 1.3 is a pretty classic problem when it comes to sequences. And it's where we give you a little bit of information, and then we want you to basically determine what else would need to be there to make this a true geometric sequence. And just like when we did this with arithmetic, we did in 1.1, is I'm going to draw it out because I think the visual helps so much. So it says that the third term is 54. So that means there's a term 1, there's a term 2, and then term 3 is going to be the number 54. Then we're going to have term 4, term 5, and then finally right here we're going to have term 6, which they give as negative 1458. Now immediately, because term 3 is positive and term 6 is negative, that does let me know that r has to be less than 0. The only way for a geometric sequence to change signs is to have a negative common ratio. Now that's a pretty broad range, right? R is less than 0 contains just a massive amount of numbers. So we have to pare it down or narrow it down just a little bit more. And just like I did in arithmetic sequences, what I'm going to do is I'm going to visualize how do I move forward in this sequence. Because it's geometric, to go from term 3 to term 4, I would multiply by the common ratio. But then to go from term 4 to term 5, I would multiply by the common ratio again. And similarly, to go from term 5 to term 6, I would multiply by the common ratio. Now, what that allows me to say is that term 6 is equal to term 3 times the common ratio once, twice, and 3 times. Now, that's fine. There's nothing wrong with writing like that, but I would rather see that term 6 is equal to term 3 times r to the power of 3. Now, when we work with that, I think visualizing this is really important. The ultimate, or what's really happening here, is to move forward in the sequence, I multiply by r. So whatever the difference in the term numbers is what exponent would go on the common ratio. To go from term 1 to term 6, I would multiply by r to the power of 5. To go from term 4 to term 6, I multiply by r squared, or to go from term 5 to term 6, I multiply by r. Now, the reason why that formula is so important, or that equation is so important, is we know term 6, and we know term 3. So I can say that negative 1,458 is equal to 54 times r to the power of 3. Now, you haven't had to solve too many equations like this. You've solved equations similar to this. The best way of doing it is to isolate the variable by dividing by 54. I'm going to need my calculator for that. That's a bit ugly for sure. So negative 1458 divided by 54, I get, a nice number, negative 27 is equal to r cubed. And I really push this concept a lot. It depends on what class you're in. You have learned an exponent rule that if you take the nth root of x, this is equal to x to the power of 1 over n. Now, the reason why I'm pushing that so much is there's two ways of approaching this last step. Most students will just jump to the idea that r is equal to the cube root of negative 27. That's fine. That'll work every time. We get that r is equal to negative 3, the cube root of negative 27. The other way of doing this, and I think this is better if you plan on taking calculus at one point, is what we're actually looking to do is get r to the power of 1 on a side. And the way that I do that is I'm going to take both sides of the equation and I am going to put it to the power of the reciprocal of the original or existing exponent. The reciprocal of 3 is 1/3. If I put both sides to the power of 1/3, I just want to show that the left-hand side is the cube root of negative 27. The right-hand side is going to be r to the power of 3 times 1/3. And I get the cube root of negative 27, which is negative 3, is going to be equal to r to the power of 1. Recognizing that radicals are just fractional exponents is a very, very important concept that we push a ton in Math 30, and we start to introduce it as well in Math 20, as you've just seen. So now we know that r is negative 3. And I know that I'm kind of, maybe we're not going to, we can just see the work. Awesome. Now, if we wanted to, we could certainly, triple check this, double check this, whatever you want to say, and I could actually just start multiplying by negative 3. So 54 times negative 3 would give me negative 162. Negative 162 times 3 would give me positive 486. Guess what 486 times negative 3 is? And it's worth checking really quickly. 486 times negative 3 is negative 1,458. All right, now I'm going to write this out just a little bit. I'm going to say that term 3 is equal to term 2 times the common ratio. That means that term 2 is equal to term 3 divided by the common ratio. And we approached this concept when we talked about arithmetic sequences. To move forward in the arithmetic sequence, you add the common difference. To move backwards in an arithmetic sequence, you subtract the common difference. For geometrics, To go forward in the sequence, we multiply by the common ratio. To go backwards in the sequence, we divide by the common ratio, which I've shown algebraically there. Now, I'm going to put them in like that. I'm going to say that term 2 is 54 divided by negative 3. When I put that into the calculator, I get negative 18. I'm going to put it down here. That means that term 1 is negative 18 divided by negative 3, which means that term 1 is 6. So just kind of summarize that term 1 is 6, and the common ratio is negative 3. These types of questions are a little bit tricky. The best thing you can do when you run into a question like this is to write it out somehow so you can visualize what's happening and then do the work after that. Definitely a bit of a tricky question though. You know, dealing with those variables to higher exponents can be tricky, which is why I like this red technique. I don't care what exponent you put on that variable, this red technique will always work. I mean, so will the black technique, but it gets a little bit trickier when this is maybe, you know, a 3/4 or some type of, you know, a little bit gnarlier fraction to work with.